It's hard to imagine that in the entire universe, Earth is the only place harboring life, especially such diverse life. Yet life on other planets might resemble what we know on Earth, or it could be radically different. Intelligent beings might look similar to humans, or they might be entirely alien. For some reason, humanity long held a stereotype of extraterrestrial life as beings with oversized heads. Whether this connects to elevated intelligence remains unknown. However, modern films and literature, following scientific developments, increasingly move beyond these established representations. And indeed, the universe is remarkably diverse. Considering the complexity of human life, the probability of similar forms emerging on planets with different physical conditions is extremely low. First and foremost, we must step outside our framework of understanding life as we know it on Earth. When we examine life on other worlds, we realize that all known terrestrial life forms exist as they do due to specific physical conditions here. The first and most obvious physical condition is gravity. For gravity on another planet to match Earth's exactly, it would need precisely the same mass and radius. For this to be possible, the other planet would likely consist of the same elements as Earth. This requires a series of additional conditions, the fulfillment of which makes finding such an Earth clone vanishingly unlikely. For this reason, if we intend to find all possible extraterrestrial life forms, we should consider their existence on planets with somewhat different gravity. Of course, gravity must be within a certain range to retain an atmosphere while not crushing the planet's inhabitants. Even within these boundaries, the most diverse life forms are possible. Above all, gravity affects the growth of living organisms. Remembering the most famous gorilla in cinema, King Kong, we should note that he wouldn't survive on Earth because he would die under the pressure of his own weight. Perhaps that's why throughout the entire film he experienced constant stress. The reason lies in the square cube law, according to which when a body doubles in size, its mass increases eightfold. Therefore, if we consider a planet with reduced gravity, we should expect to find larger life forms. We also understand that bone and muscle strength depends on gravitational force. Recalling another example from the animal world, the blue whale, if it ends up on land, the whale suffocates. However, this doesn't happen because it suffocates like a fish. Whales are mammals, breathing with lungs just like people. The poor creatures die because gravity prevents their lungs from expanding. From this, it follows that under conditions of increased gravity, humans would possess stronger bones capable of supporting body mass, more powerful muscles capable of counteracting gravitational force, and smaller stature to reduce body mass according to the square cube law. The physical characteristics of the body dependent on gravity are merely our understanding of gravitational influence on organisms. In reality, gravity can determine a significantly broader range of body parameters. Another global physical condition determining the form of living organisms is atmosphere. By requiring an atmosphere, we consciously narrow the circle of planets with the possibility of life, since we cannot yet imagine organisms capable of surviving without atmospheric support and under the deadly influence of cosmic radiation. Therefore, let's assume that a planet with living organisms must possess an atmosphere. Consider insects, whose size is clearly limited due to their respiratory system. It doesn't include lungs and consists of tunnel-like tracheae exiting outward as openings. Such oxygen transport doesn't allow for mass exceeding 100 grams because at larger sizes it loses effectiveness. However, during the Carboniferous period, approximately 350 million years ago, our planet was saturated with elevated atmospheric oxygen, approximately 35%. the animals and insects of that time could surprise you. Gigantic air-breathing insects. A dragonfly could have a wingspan exceeding 65 centimeters. A scorpion reached 70 centimeters. A millipede could be 2.5 meters long. Who would be chasing whom is debatable. Thus, the influence of oxygen concentration in the atmosphere on various life forms becomes obvious. Moreover, the presence of oxygen isn't a determining condition for life's existence, since we know of anaerobes, organisms capable of living without consuming oxygen. Then, if oxygen's influence on organisms is so significant, what would life forms be like on planets with completely different atmospheric compositions? This is difficult to imagine, but it would look terrifying. So before us arises an unimaginably large set of life forms that might await us on another planet, considering only these two factors. If we also consider conditions like temperature or atmospheric pressure, the diversity of living organisms exceeds the limits of perception. But even in this case, we shouldn't fear making bolder assumptions defined in alternative biochemistry. Many are convinced that all life forms can exist only if they contain carbon, as we observe here on Earth. However, we must understand that the building block of alien life might not be carbon at all. Among alternatives to carbon are silicon, nitrogen, and phosphorus, or nitrogen and boron. Silicon is considered the most likely candidate for structure-forming atoms in alternative biochemistry. Its properties are in many ways similar to carbon, but silicon atoms have greater mass and radius. They form double or triple covalent bonds with more difficulty. Yes, this might hinder the formation of biopolymers, polymers that are part of living organisms. Although the main hypotheses of non-carbon extraterrestrial life forms are based precisely on silicon, such life would probably have much less diversity than carbon-based life, since silicon compounds cannot be as diverse as carbon compounds. But still, this is possible. And if so, then silicon-based life could differ so greatly from what we're familiar with that we can barely fantasize about what silicon aliens might look like. Certainly not big-headed, bug-eyed little humanoids. Ammonia, like water, is a polar molecule capable of dissolving a wide spectrum of organic compounds and participating in diverse chemical reactions. The external appearance of hypothetical life forms based on it will depend significantly on the specific ecological and evolutionary factors of their native world. Predicting what they might look like remains challenging within our current scientific understanding. However, we can consider ammonia's properties. Ammonia life forms could thrive in extremely cold environments where ammonia remains liquid, since it has a lower freezing point than water. This could affect their biochemistry, possibly leading to slowed metabolic processes compared to terrestrial life forms. Their cellular biology could also differ significantly, since structures that evolved to contain and isolate chemical reactions in an ammonia environment might differ from the lipid membranes we see in terrestrial organisms. Ammonia creatures would most likely possess slowed metabolism and would live long, possibly happy lives, but their transformation would proceed slowly. On the other hand, low temperatures would allow these creatures to absorb chemical substances too unstable at terrestrial temperatures. Ammonia life forms would most likely seem unpleasant to us because they would emit a rather foul smell. However, this isn't so important, since at Earth temperatures, the poor things would almost instantly evaporate. Interestingly, the concept of sulfur-based life is also fairly realistic for alternative existence. This element is key to a number of life processes on Earth, which makes it plausible to consider its role in alien organism biochemistry. The concept suggests that such organisms could obtain energy through the oxidation of sulfur and sulfur-containing compounds, making them quite hardy, unlike fragile humans. One of the most likely candidates in our solar system for sulfur-based life is Jupiter's moon, Io. The intense volcanic activity of this satellite has led to significant sulfur deposits on its surface. Potential organisms inhabiting planets or satellites like Io would breathe sulfur monoxide, which functionally would be analogous to our oxygen. However, under conditions of sharp temperature fluctuations, the almost complete absence of water, and intense radiation from Jupiter, life as we understand it could hardly be preserved there, although something like a fungus might still inhabit it. The main thing is that it doesn't get aboard our spacecraft. Of course, not all inhabitants of fantastical worlds will agree that life is only a chemical phenomenon, and most likely they'll be right. In science fiction classics, creatures consisting of magnetic fields, hot plasma, thinking oceans, or clouds of gas drifting in space are mentioned. A common feature of all non-chemical creatures is their mysterious and most likely artificial origin. A being endowed with reason doesn't appear randomly. The complex must form from the simple. But it's unclear what would be the carrier of heredity in a clot of plasma, and how a cloud of gas or ocean could be subject to mutations and natural selection. Although we haven't yet discovered confirmed extraterrestrial life, numerous discoveries such as water on Mars, potentially habitable exoplanets, and organics on comets give promising clues that life might exist somewhere else. Moreover, technological progress constantly improves our means of research and detection, which inspires optimism that the discovery of extraterrestrial life is possible. Moving forward in our searches, we should remember the famous words of Carl Sagan. Imagination often takes us to worlds that never were, but without it, we go nowhere. In this context, speculative biology isn't just reasoning about life beyond Earth. Such a discipline develops our scientific imagination and thereby directs our aspiration to knowledge. Sciences such as astrobiology, exobiology, or xenobiology study hypothetical life forms that could arise and exist beyond our planet. Such extraterrestrial life can vary from simple single-celled organisms to creatures with civilizations possessing advanced intelligence, possibly far more developed than humanity. However, today we won't leave the boundaries of the solar system, but will examine what we know about life in all its manifestations on nearby planets and their satellites. Well, let's begin our transit from the Sun to the outermost planet of our system. Before us is Mercury, the closest planet to the Sun, too hot on one side and too cold on the side opposite the star to support life. It may have a thin oxygen atmosphere, but it's still critically insufficient for the formation and maintenance of living things. But what if deep underground there could be life forms, some extremophile microbes? Yes, this is possible, but extremely unlikely. The fact is that the side of Mercury facing the Sun will be too hot, and the side facing away will be too cold. All creatures face either nightmarish heat or eternal frost. With such prospects, survival is difficult. Next, Venus, the second planet from the Sun, whose size and structure are similar to Earth. However, it has an important difference: a surface hot enough to melt lead, not to mention living organisms, a crushingly heavy atmosphere, and active volcanic geology. Venus began its existence much like Earth, perhaps even with oceans and all the possibilities for life on the surface. But the two planets went completely different paths. An uncontrolled greenhouse effect probably vaporized any inhabitants and turned it into an inferno. This is a clear picture of how terrestrial planets can burn. However, despite the harsh living conditions, researchers aren't dismissing this planet. At an altitude of 50 to 60 kilometers, the gas phosphine was discovered. Its concentration was small, slightly higher than methane on Mars, but the very fact of its detection is significant. Quite a lot was written that this could be a probable sign of life, little green microbes literally right next door in orbit. It's worth figuring out why. First, phosphine is chemically active. It decomposes at elevated temperatures into pure phosphorus and hydrogen, the atoms of which it consists. Second, phosphorus after this, in the conditions of Venusian clouds, should simply fall down where there's no hydrogen. That is, from the places where terrestrial telescopes noticed it, phosphine should constantly disappear. Third, what's especially important, on Earth, this gas before the appearance of humans was formed in only one way, as a result of the activity of anaerobic bacteria. But where would they come from in Venus's atmosphere? Could other civilizations have gotten ahead of us and begun terraforming? That would be wonderful, but it's unlikely. Is the formation of phosphine possible through non-biogenic means? Yes, theoretically, phosphine on Venus could be ejected by volcanoes and have no relation to life. But still, such a find is quite interesting. Meanwhile, we're heading toward Mars, another potentially habitable planet in the past. Just like Venus and Earth, it's located in the star's habitable zone. In a certain sense, the red planet tells a repeating story. Evidence on the surface confirms that Mars was once wet, with rivers, lakes, and possibly even oceans. Then, solar wind and radiation carried away most of its atmosphere, and its minimally active core stopped generating a protective magnetic field. The surface of Mars became impregnable and dry. Is there anything alive left on Mars? Excavations are needed. Maybe we'll find evidence of past life, or at least fossils, possibly under the surface or in frozen polar caps. The main problems on the path to life are the lack of accessible water and the absence of plate tectonics, a process on Earth that moves continents over epochs and transfers buried nutrients back to the surface. In favor of Martian life, we can include the detection of methane in the Martian atmosphere. On Earth, methane is replenished through the metabolic action of various life forms. Methane can also form as a result of the reaction of water and rock. But microbial life beneath the surface is another possibility that shouldn't be dismissed. And how can we not mention the organics found on the red planet by the Curiosity rover? Both aliphatic and aromatic compounds were found here, as well as thiophene derivatives, a cycle containing 4 carbon atoms and 1 sulfur. Why is this so important? On Earth, thiophene can be found in coal and crude oil, products of biogenic origin. Moreover, they're produced by some microbes and fungi. But still, there's a probability that Martian molecules have a non-living nature and formed as a result of geochemical processes. The future ExoMars mission could better clarify the situation. A fundamentally important device of the future rover is a drill with a maximum working depth of up to 2 meters. At the moment, its launch has been postponed until the late 2020s. Continuing our journey in search of life, we're approaching the majestic giants of the solar system: Jupiter, Saturn, Uranus, Neptune. Their chains of moons can be considered almost independent solar systems, and some of these satellites could quite possibly be habitable worlds. Europa, Jupiter's satellite with an icy shell that seems completely lifeless. However, beneath the frozen surface, space probes have discovered evidence of a huge ocean of liquid water. On 2 other satellites of Jupiter, Ganymede and Callisto, there are probably also underground oceans, although they might be sandwiched between layers of ice, making life less likely. But Europa has good contact between the liquid water ocean and the rocky interior. This means that mineral compounds are washed out, supplying resources for living organisms, or perhaps alien marine life, if it exists there. In addition, traces of hydrogen peroxide have been noticed, which is necessary for methane formation by anaerobic archaea. Besides resources like peroxide, thermal energy is also needed for the existence of life, and it's most likely also present on Europa. Thanks to tidal forces, internal layers shift and deform under the influence of gravity. All this leads to friction with heat generation. The mantle of Jupiter's moon heats up, which warms the layers of the ocean. It's probably warmest at certain depths, where the maximum volume of heat is generated, meaning something alive might definitely be there. Since oxygen is most likely formed on Europa's surface under the influence of solar wind and then enters the ocean during geological processes, the concentration of oxygen in water is currently impossible to determine precisely. As for life itself, it's believed that chemotrophic bacteria would be at the base of the food chain. They would form layers of organic deposits on the ocean floor, and other living organisms would feed on these deposits. These creatures would be the analog of herbivorous organisms on Earth. Potentially habitable worlds can also be found among Saturn's satellites. Enceladus, although tiny, also hides an ocean of liquid water under an icy shell. This satellite sends free samples from its ocean into space, and this is the only place in the solar system with guaranteed access to an underground ocean without the need to drill through kilometers of ice. The Cassini probe once flew through such a plume. Unfortunately, no microbes were found, but it still discovered important clues for us. These include complex organic molecules, salts similar to those contained in Earth's oceans, and silicate nanocrystals. Then there's Titan. Although it's smaller than Earth and has less gravity, Titan resembles our own world in some ways. Nitrogen dominates the atmosphere of this moon, just as in Earth's atmosphere. Titan is the only body in the solar system beyond Earth with rain, lakes, and rivers. Essentially, it's a whole hydrological cycle, except its flowing bodies of water consist of hydrocarbons, methane, and ethane. Titan also has a subsurface ocean of water, although deep below, and it's unknown whether the ocean makes contact with anything from the surface. If this happens, mixing with the complex chemistry on the surface could provide fuel for life. If not, there's another possibility. The chemical mixture on the surface could feed life such as we don't yet know, exotic forms based on completely different components and chemical reactions. True, the strong cold on Titan's surface certainly means that chemistry happens very slowly. Is there a probability that a species similar to us inhabits somewhere else? If we draw conclusions based on modern science, the chances of meeting intelligent neighbors are uncertain. The presence of a self-aware life form is influenced by many factors: planet size, gravity, atmosphere, flora, fauna, distance from the star, and countless other reasons. Most likely, intelligent biological life forms on other planets, if they exist, look and are structured completely differently. And even if they have some similar features with humans, genetically, they're still incompatible with us. Perhaps it's silicon-based life, synthetic or cybernetic life. Maybe their development was influenced by quantum phenomena, or perhaps it's an inorganic chemical phenomenon. This is just a small part of what's known to us in the vast universe. Now, let's take a creative detour and explore how science fiction has imagined alien life, particularly in the cosmic horror of Howard Phillips Lovecraft, whose creatures, while fantastical, sometimes align eerily with what xenobiology suggests might be possible. Even in childhood, Howard was fascinated by history, chemistry, and especially astronomy. He began publishing articles dedicated to his scientific research. At first, Lovecraft's articles were quite childish, but soon serious publications noticed him. Already in 1906, his astronomy article was published by a famous newspaper. Then Howard became a permanent host of an astronomy column. At this same time, he began his literary activity, combining knowledge about space with his own nightmarish dreams and imagination. In 1917, The Tomb and Dagon came out. Then, Beyond the Wall of Sleep, The Transition of Juan Romero, and other works. In Lovecraft's world, the insignificance of humanity is constantly emphasized in the face of cosmic horror. Attempts to comprehend the true nature of the world, or even counteract the sinister forces hiding behind the scenes, mostly end tragically. Lovecraft's universe represents a supernatural interweaving of horror and fiction. The essence is one. Humanity isn't alone in the universe. Moreover, even on our small planet, it became the dominant species by pure chance, meaning its well-being is under constant threat. In the universe, there are creatures capable of moving through cosmic space and colonizing various planets. At different periods of its history, Earth was a haven for several species of such creatures. In the human epoch, some have already died out, others are waiting their time, and still others continue to hide in hard-to-reach corners of the world. Let's meet a few creatures from Lovecraft's fantastic world. The Bi-Ahki, an interstellar creature consisting of ordinary matter. From the chest stretch 2 wings, 2 limbs, and a head. Their habitat is predominantly airless planetoids and comet cores. They enter atmospheres only to hunt. They reach Earth too, but don't live here. They usually feed on interplanetary life forms, which are rare in the solar system, but can also devour Earth's inhabitants with alarming regularity. The Doles are colossal worm-like organisms. They avoid light, living underground, so they're rarely seen. A Dole can release a stream of poisonous acidic slime from its mouth. A typical specimen is at least 180 meters long and 6 meters thick. The giant never crawls to the surface until it riddles and destroys a certain section of crust. The Dole's tunnels, stretching in all directions, form a terrible labyrinth. The huge worm feeds on hydrocarbons of all types, including coal, oil, and corpses of ancient creatures. The elder things appear half plant, half animal, resembling a sea lily with a star-shaped head, with a barrel-shaped body, many tentacles, and 5 wings. These individuals are remarkable for their strict radial symmetry. Their habitat is the ocean floor of satellites of gas giants or distant ocean planets. They can produce food from inorganic substances, but become more active when feeding on living organisms. They move with great speed on land, water, and air. The elder things are extremely hardy and can survive at any temperature. Then there's Azathoth. It usually resides outside space and time at the center of the universe, but can appear anywhere if necessary. Since Azathoth has existed since the very beginning of time, it was able to spawn some worlds independently. This creature is blind and mindless in our understanding, infinitely powerful. We've examined far from all the alien creatures, only a small part of them. And yes, this is just Lovecraft's fantasy. But who says these creatures or beings similar to them in distant worlds of our vast universe are so unrealistic? Howard Phillips Lovecraft clearly showed us that the development of science and technological progress not only doesn't make humanity more protected, but brings it closer to mysteries from the unknowable and unrecognizable. Unrecognized during the writer's lifetime, he inspired many authors in popularizing interstellar concepts, not to mention numerous literary works, film adaptations, and computer games. In every third Lovecraft story, one or another non-human race is described: deep sea dwellers, those living on comets, or those inhabiting the atmosphere. Within the framework of cosmic horror, these creatures acquire a completely different, ominous coloring. And who knows, maybe at the edge of the universe, similar creatures have already lived for millions of years, and fortunately, we don't even suspect their existence. The question of whether humanity is alone in the vast cosmic expanses has troubled our species since we first looked at the starry sky. Perhaps somewhere out there, far away, in orbit around distant stars, there are living worlds. What makes people think they're not alone in the universe? And why does the search for extraterrestrial life concern not only science fiction writers and scientists, but also ordinary people? Concentration on this is due to a whole range of factors, starting with the astronomical number of stars and planets, and ending with ancient legends woven into history. Something tells us that somewhere out there, other intelligent life forms must exist. Perhaps silicon-based or synthetic life based on methane or other biochemical variants. Yes, their physical features, thinking, communication, and reproduction methods will remain a mystery for us, probably for a very long time. However, despite the absence of confirmed extraterrestrial contacts, belief in our interstellar neighbors remains a resonant feature of human existence. In different cultures, the incomprehensibility of space evoked a common sense of wonder, as well as suspicion that in it there must be something more than meets the eye. After all, humanity to this day has examined only a drop in the ocean of space. There are enough reasons why people believe they're not alone in the universe. This is the scale of our enormous cosmos. The universe is incomprehensibly huge and may even be infinite. It contains billions of galaxies, each of which contains billions of stars. The number of planets in the universe is almost incomprehensible. Even in our own Milky Way galaxy, it's estimated there are up to 100 billion planets. Simply the law of large numbers suggests that with such a quantity of opportunities for life's emergence, it's statistically unlikely that Earth is the only place where it exists. Secondly, in recent decades, thousands of exoplanets have been discovered beyond the solar system, some of which are located in the habitable zone of their stars, where temperature and other conditions allow the existence of liquid water. Achievements in astronomy and astrophysics have revealed the possibility of habitable conditions on moons and planets within the solar system, such as subsurface oceans on Jupiter's moon Europa and Saturn's moon Enceladus. Moreover, water may not be the main factor, since life can develop differently. Thirdly, the diversity of life on Earth itself. The discovery of extremophiles, organisms capable of surviving in extreme conditions, has expanded the range of environments in which life can exist. These can be the most extreme and diverse conditions, from deep-sea hydrothermal vents to acidic hot springs, from cold tundras to dry hot deserts. Such resilience and adaptation of life on our planet allows us to assume that life could take hold in other conditions as well. That's why astrobiology appeared, a scientific discipline considering the possibility of the emergence, evolution, and preservation of life on other planets. Astrobiologists study the conditions necessary for life, search for biosignatures on other planets, and develop methods for detecting extraterrestrial organisms. This field combines knowledge from biology, chemistry, geology, and astronomy to answer one of humanity's most profound questions: are we alone? Fourth, throughout history, many cultures have developed myths, legends, and religious beliefs about beings from the heavens. From ancient Sumerian texts to Native American stories of star people, the idea that we're not alone has deep roots in human consciousness. These narratives, while not scientific evidence, reflect a persistent human intuition that the cosmos might harbor other forms of intelligence. Fifth, the Fermi paradox keeps this question alive. Named after physicist Enrico Fermi, who famously asked, "Where is everybody?" This paradox highlights the contradiction between the high probability of extraterrestrial civilizations existing and the complete lack of evidence for or contact with such civilizations. The paradox has spawned numerous hypotheses. Perhaps intelligent life is extremely rare. Perhaps civilizations destroy themselves before achieving interstellar travel. Perhaps they're deliberately avoiding us. Or perhaps we simply lack the technology to detect them. Sixth, the search for extraterrestrial intelligence, known as SETI, has been systematically scanning the skies for signals from alien civilizations since the 1960s. While no confirmed signals have been detected, the very existence of such projects lends scientific credibility to the search and keeps hope alive. Programs like Breakthrough Listen have brought new resources and attention. The famous WOW signal detected in 1977, though never repeated or explained, remains a tantalizing hint of what might be possible. Seventh, recent discoveries of organic molecules in space, including amino acids on comets and complex carbon compounds in interstellar clouds, demonstrate that the building blocks of life as we know it are widespread throughout the universe. Eighth, mathematical models suggest we're not alone. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to estimate the number of active extraterrestrial civilizations in the Milky Way galaxy. While the equation contains many unknown variables, most versions suggest at least a possibility of other civilizations existing. Recent revisions, taking into account updated knowledge about exoplanet frequency and habitability, generally increase the estimated number of potential life-bearing worlds. Ninth, the rapid pace of technological advancement gives us hope that detection is just around the corner. Each new generation of telescopes, from the James Webb Space Telescope to future projects like the Extremely Large Telescope, brings unprecedented capabilities for analyzing exoplanet atmospheres and searching for biosignatures. Improved spectroscopy techniques may soon allow us to detect the chemical fingerprints of life in the atmospheres of distant worlds, such as the simultaneous presence of oxygen and methane in proportions that suggest biological activity. 10th, there's a psychological dimension to this belief. The idea that humanity is utterly alone in the cosmos can feel isolating and existentially troubling to many people. Believing in the possibility of other intelligent life provides a sense of cosmic companionship and suggests that consciousness and intelligence are fundamental features of the universe rather than cosmic accidents. The scientific search for extraterrestrial life operates on multiple fronts. Astrobiologists study extreme environments on Earth to understand the limits of life. Planetary scientists examine our solar system's moons and planets for signs of past or present life. Astronomers catalog and characterize exoplanets, looking for Earth-like worlds. And SETI researchers scan the electromagnetic spectrum for artificial signals. Each approach contributes pieces to the larger puzzle. Consider Proxima Centauri b, an exoplanet orbiting our nearest stellar neighbor, just over 4 light-years away. Discovered in 2016, this world orbits within its star's habitable zone and could potentially harbor liquid water on its surface. However, Proxima Centauri is a red dwarf star known for violent flares that could strip away any atmosphere the planet might have. Does this make life impossible? Not necessarily. Life could exist in subsurface oceans, protected from radiation. Or organisms there might have evolved radiation resistance far beyond anything we see on Earth. The point is that each new discovery raises more questions than it answers and expands our understanding of where and how life might exist. The concept of habitable zones has itself evolved. Once, we thought only planets at a certain distance from sun-like stars could support life. Now we understand that tidal heating can warm moons of gas giants far from their stars, that thick atmospheres can create greenhouse effects making cold worlds warm, and that subsurface oceans can exist almost anywhere. The definition of habitability keeps expanding as our knowledge grows. Let's also consider the Great Filter hypothesis, one proposed solution to the Fermi paradox. This idea suggests there's some barrier that prevents life from commonly reaching advanced, spacefaring civilizations. The terrifying question is whether this filter lies in our past or our future. If it's in our past, perhaps the emergence of life itself is extraordinarily rare, or the jump from simple to complex cells almost never happens, or intelligence rarely evolves. In this case, we might be one of the few civilizations to have made it this far, which would be simultaneously special and lonely. But if the Great Filter lies in our future, it suggests that something typically destroys civilizations before they achieve interstellar travel. This could be nuclear war, environmental collapse, artificial intelligence gone wrong, or some other catastrophe we haven't yet imagined. In this darker scenario, the silence of the cosmos might be a warning. Many civilizations have arisen, but none survive long enough to spread among the stars. Another fascinating possibility is the zoo hypothesis, which suggests that extraterrestrial civilizations are aware of Earth and humanity, but deliberately avoid contact, perhaps to allow for natural evolution and cultural development, much like researchers observing animals in a wildlife preserve without interference. This could explain why, despite the potential abundance of alien civilizations, we've detected no clear signs of them. They're watching, but from a distance, waiting for us to reach some threshold of development before making contact. The rare Earth hypothesis argues that while simple microbial life might be common in the universe, complex multicellular life, and especially intelligent life, requires such a specific and unlikely combination of factors that it might be extremely rare. Earth's large moon stabilizing its axial tilt, its position in the galaxy's habitable zone, Jupiter's role as a cosmic vacuum cleaner protecting us from asteroid impacts, the presence of plate tectonics recycling nutrients, and dozens of other factors all had to align just right. Perhaps we're not completely alone, but our nearest intelligent neighbors might be so far away that communication is impossible. Recent developments in artificial intelligence have also influenced this discussion. Some theorists suggest that biological intelligence might be merely a brief phase in the evolution of consciousness in the universe. Perhaps most advanced civilizations quickly give rise to artificial superintelligences that then become the dominant form of mind in the cosmos. If this is true, we might be searching for the wrong kind of signal, looking for biological beings when we should be looking for signs of vast computational substrates or other forms of machine intelligence. The question of what extraterrestrial life might actually look like has evolved dramatically. Early science fiction often depicted aliens as humanoid, but modern astrobiology takes a much broader view. On a high-gravity world, life might be low and squat, built close to the ground with powerful support structures. On a low-gravity moon, creatures might be tall and spindly, or perhaps they'd fly through dense atmospheres with ease. In dark ocean worlds beneath ice shells, life might rely on chemosynthesis rather than photosynthesis, building ecosystems around hydrothermal vents with no light required. Imagine a world orbiting a red dwarf star where dim red light might favor photosynthetic organisms that appear black to human eyes, absorbing every possible photon. or a tidally locked planet with one side always facing its star, creating a permanent day side and night side with a narrow habitable ring between them where life clusters, or ocean worlds where intelligence evolved in three-dimensional aquatic environments, giving rise to minds that think in ways utterly foreign to terrestrial land dwellers who evolved in essentially two-dimensional environments. Some researchers have even explored the possibility of plasma-based life in stars, or electrical life in planetary magnetospheres. While highly speculative, these ideas push the boundaries of what we consider alive. If consciousness can emerge from the electrochemical interactions in biological brains, why couldn't it emerge from other complex systems? The universe might be far stranger and more alive than we imagine. The timeline question is also crucial. The universe is 13.8 billion years old. Earth is only 4.5 billion years old. Billions of years before our solar system formed, other star systems with planets existed. If life emerged on any of those worlds and some civilization survived, they could be billions of years more advanced than us. What would a civilization with 1 million years of technological development look like? Or 10 million? Or 1 billion? Such beings might be so far beyond us that we couldn't recognize their works as artificial, mistaking their megastructures for natural phenomena. This leads to the concept of Dyson spheres, massive structures that could encompass entire stars to capture their energy output. Some astronomers search for the infrared signatures such structures would produce. Others look for signs of stellar engineering, stars with unusual dimming patterns that might indicate something is being built in orbit. The star known as Tabby's star showed strange, irregular dimming that briefly sparked speculation about alien megastructures, though natural explanations involving dust clouds now seem more likely. Still, the fact that we're looking for such things shows how seriously science takes the possibility of advanced alien civilizations. We must also consider the timescale problem. Civilizations might arise, flourish, and fall over thousands or millions of years. Two civilizations might exist in the same galaxy, but be separated by such vast time periods that they never overlap. We might be receiving signals from civilizations that died out millions of years ago, or we might be broadcasting into space that won't be heard for millions of years by civilizations not yet born. The cosmic ocean is vast, not just in space, but in time. There's also the question of what constitutes life and intelligence. We define these terms based on Earth's examples, but the universe might contain forms of organization, complexity, and awareness that don't fit our categories. Could a planet-spanning fungal network be considered a single intelligent organism? Could the interaction of magnetic fields and plasma in certain environments give rise to information processing and self-awareness? Our search strategies assume aliens will be somewhat like us, but this might be a profound limitation. Language and communication present another challenge. Even on Earth, we struggle to communicate with dolphins and whales, fellow mammals with complex brains and social structures. How would we communicate with an alien intelligence that evolved in a completely different environment with different sensory organs and a different evolutionary history? They might communicate through color changes, electrical fields, chemical signals, or methods we haven't imagined. Even if we detect a signal, decoding it could be impossible without some kind of universal mathematical or physical principles to serve as common ground. The search continues on multiple fronts. Radio telescopes scan the skies. Spacecraft explore our solar system. Advanced telescopes characterize exoplanet atmospheres. Each year brings new discoveries and new questions. We find more potentially habitable worlds. We learn more about the resilience and adaptability of life. We develop better tools and methods for searching. Perhaps the answer to whether we're alone will will come not from detecting alien signals, but from finding microbial life in our own solar system. If we discover that life arose independently on Mars or Europa or Enceladus or Titan, it would suggest that abiogenesis, the emergence of life from non-living matter, happens readily when conditions are right. This would imply that the universe is teeming with life, even if intelligent life remains rare. Or perhaps we'll find biosignatures in the atmosphere of a nearby exoplanet, oxygen and methane in combinations that suggest biological activity. Or perhaps our artificial intelligence systems will detect patterns in radio noise that human analysts missed, patterns that encode a message from the stars. Or perhaps nothing will happen for generations, and the search will continue into humanity's distant future. What's certain is that the question matters deeply to us. Are we alone? The answer will fundamentally shape how we understand our place in the universe. If we're alone, we're cosmically precious, perhaps the only witnesses to the universe's existence. The responsibility to preserve life and consciousness would rest entirely on our shoulders. If we're not alone, it changes everything. Our philosophy, our sense of identity as a species. We would know that intelligence and consciousness are woven into the fabric of the cosmos, that we're part of a greater community of minds. So we keep searching, keep wondering, keep looking up at the stars. The silence might be temporary. The answer could be in the next discovery, orbiting the next star. Whether we find alien microbes on Europa, detect biosignatures on distant exoplanets, or remain alone for now, the search itself transforms us. It pushes our technology, expands our imagination, and reminds us that we're part of something far greater than ourselves. The question isn't just, are we alone? It's, what does it mean to be alive in this vast, mysterious cosmos? And that question is worth more than any answer we might find.